Efficient water management has become a critical challenge in a world where the scarcity of this resource is increasingly evident. One of the strategic priorities on the international agenda is to address water scarcity due to the increasing drought caused by global warming in recent years. Therefore, it is essential to generate new alternatives that are self-sustainable and energy efficient. The development of devices that use the Peltier effect for water condensation has aroused great interest. These devices, based on the physical principle discovered by Jean Peltier in 1834, use thermoelectric modules to create temperature gradients that allow water vapor from the environment to condense. These devices offer several advantages, including a compact design and the ability to operate in various environmental conditions. However, challenges such as energy efficiency need to be addressed by optimizing condensation design. In this project, Peltier cells are put into use to collect water through condensation. These cells, which work through the thermoelectric effect, create a temperature difference when an electric current is applied to them. This difference can cool a surface enough to condense water vapor present in the air, transforming it into liquid water that can be collected. By applying this principle, atmospheric moisture can be captured and used efficiently, offering a viable alternative for recovery areas. Peltier cells, also known as thermoelectric modules, are devices designed to generate rapid and precise cooling or heating depending on the applied electrical current. These cells are composed of two P and N-type semiconductors, joined together by thermoelectric junctions. When an electrical current is applied to the cell, electrons move within the material and generate thermal energy in the form of heat or cold, depending on the direction of the current. Basically, an electric current flows through the junction of two different metals. A temperature difference is generated at the junction. In the case of Peltier cells, this junction is formed by two semiconductors with different doping levels, which creates a temperature gradient in the cell when an electric current is applied. To develop the experiment, as a first step, a Peltier cell will be implemented inside two commercial heat sinks with an output power of 30 W at room temperature. Preliminary results from a commercial heatsink show a condensation rate of 4 to 8 milliliters on a surface area of 16 square centimeters. We build a circuit using temperature sensors for our database to monitor the behavior of the temperature, both in the heatsink and in the cold one. In this way we realize that the cold sink must be thin and with the same dimensions of the cell, in addition to the importance of the thermal insulator around the cell to avoid the interaction of both temperatures. To achieve better results, modifications in the geometry of the heatsink were explored using different generative designs and additive manufacturing techniques. As you can see, some images are integrated here in which different designs are observed. We can even see a circular one. To maximize the effectiveness of this technology, 3D printing and the use of specialized additive manufacturing software such as NTOP are integrated into the design and manufacturing of the capacitor elements with aluminum, to which a percentage of carbon nanotubes is added. This technique allows the creation of complex and personalized structures, improving the efficiency of the condensation process and optimizing water capture. The ability to design innovative geometries adapts specific needs, since we must find a balance that provides us with the ideal conditions for condensation, since in the first tests the amount of water is minimal and very slow. 12 tests were carried out, in which changes and improvements were progressively made with both 3D printing and additive manufacturing, improving heat distribution and reducing the use of material by allowing the creation of complex and personalized internal structures, such as flow channels of air for the heat sink and optimized geometries. These advanced structures improve the efficiency of thermal transfer, distributing heat more uniformly and effectively, while additive manufacturing allows only the necessary amount of material to be used. Weather conditions affect the performance of a heatsink in several ways. At higher ambient temperatures, the capacity of the heatsink to dissipate heat decreases, since there is a large temperature difference between the heatsink and the environment, reducing the efficiency of thermal transfer. This is a problem that is being reduced with the various models used. Other materials such as copper have also been used, but we observed less condensation, so it is not a good option. It is also worth mentioning that these condensing models have features that would improve cooling systems and compact cooling systems, which are used in many different sectors. On this side, we can see the graph of the increase in condensation, humidity monitoring and ambient temperature of all the tests carried out. We went from condensing 1 milliliter in the first test to condensing 33 milliliters in the last one, in which the last design was printed as a prototype using resin printing, to which a percentage of carbon nanotubes was added. Condensation. To be efficient, the heat condenser must be kept at room temperature. It should be noted that the model behaves differently in different regions. In this case, the room temperature ranges from 16 to 27 degrees Celsius. It is worth mentioning that Peltier cells have several advantages, such as their compact size, fast response, and precise heating capacity. Additionally, they contain no moving parts or coolants, reducing the risk of leaks and increasing reliability. The ideal temperature of the cold condenser to maintain a constant drip and ensure that the water droplets do not freeze ranges from 4 to 8.3 degrees Celsius. The model has greater efficiency when working at night, since that is when there is greater humidity and lower ambient temperature, therefore greater condensation. Depending on the dimensions of the heatsinks, the maximum and minimum temperatures they can reach will be. The reduced size of the cold sink allows the temperature to be distributed proportionally over the entire surface. The design allows you to take advantage of the area, giving enough space for the accumulation of more water droplets, and the inclination guarantees constant production and dripping. The design of the heatsink allows the fan to dissipate the temperature in a more regulated manner, reducing the difference between temperatures in the center with respect to the edges. Finally, the results of the experiments with common heatsinks led me to a next proposal for a capacitor model. This can be seen in the image on the right, which has been designed using specialized additive manufacturing software NTOP. Thanks to its geometry, it can be, in other words, it will not only improve thermal distribution, but also reduce the amount of raw material, since each layer measures 1 mm thick and its flow channels will allow air to recirculate and therefore a higher level of condensation. In conclusion, water condensation through the Peltier effect represents a promising innovation with the potential to address water access challenges around the world, offering a sustainable and above all scalable solution, since with our experiments we increased the cup by 4 times of condensation on a smaller surface, all of this in order to improve the quality of life of vulnerable communities. This research will now take the next step with the use of generative design software, with the aim of meeting the design requirements and having full control of the geometry required to maximize the condensation power of our model.